When you have a second order system, you can show that. For example, you might say, what do you mean by second order system? I mean like the governing differential equation is second order, or if you basically find the transfer function, the denominator is a polynomial that is quadratic in terms of S. So like an RLC circuit or a mass spring damper system. You can show that here the output over input for the electrical circuit, it is the output voltage over input, or for the mass spring damper system, it is the position of the block over the external force. You can show that in general. You can write it this way as omega n squared over s squared plus 2 zeta omega ns plus omega n squared, where omega n, we call it the natural frequency of the system, and zeta is called damping ratio. Zeta in general is any number, it could be, okay, and based on how the zeta is, whether it's less than 1, it's bigger than 1, or equal 1, then I'll show you we have different types of responses for the system. Now, so let's see that. So if we allow this system to be exposed to a step input, unit step input, so U of S is equal 1 over S, then Y is G times U, so it's 1 over S times the second order system. And then if now you have to do partial fraction and find the answer, first of all, if you want to know the steady state error, remember that the steady state in general always was S U of S times 1 minus G of S for any arbitrary G and U. So if you plug in the G and U in this case, you can easily find that the steady state error is 0. In other words, the system is well capable of what? Catching up with the step input. And that was the same for the first order system. If you remember, the first order system had also what? 0 steady state error in response to step input. And of course, second order system can do that too. In general, the higher the order of the system is, the better it can catch up with primary inputs, okay? So remember that first order system could easily catch up with the step, but it could not completely catch up with the ramp, right? There was always a gap of t units. Now I'll show you here that the second order system can actually catch up with both. Catch up with the step and ramp. So first let's look at the step input. So there is no steady state error, but now the type of response, Y, it depends on the value of zeta. Basically, it depends on whether this denominator here has real roots, imaginary roots, or what? Or basically just two real roots that are repeated, identical, correct? Because as I said, you have to do partial fraction here. And when we want to do partial fraction on this, if you remember from what we had in the past, is let's see. See if I can make this bigger for you. Oh, okay, it's not gonna keep it so nice. I'll write it this way. So your Y of S is 1 over S times omega n squared divided by S squared plus 2 zeta omega ns plus omega n squared. So when you want to basically do partial fraction on this, it is going to be some number over S plus. Now, how would you decompose the second part? You have to look at the roots of this. And the roots of this in general are what? S1 and 2 is equal to negative b plus minus square root of b squared minus 4 times a times c. divided by 2a, which if you look here inside this square root, this is going to be 4 zeta squared omega n squared. This is 4 omega n squared. So you can factor out a 4 omega n squared out of it, and then it is going to be zeta squared minus 1. Okay? And then this 4 omega n squared comes out of the square root, becomes 2 omega n, and this guy also has 2 omega n. So you can factor out the 2 omega n's, cancel out the 2. So if you see that and you want to simplify it, it is basically going to be negative zeta omega n plus and minus what? Omega n times square root of zeta squared minus 1. Okay, so these are your roots, and depending on whether they are imaginary, they are real, or they are the same thing, then you have different scenarios. So when is it that you can have real roots? When, of course, zeta is what? Zeta squared minus 1 is bigger than 0. So, right, when zeta, absolute value of it, is bigger than 1, then, of course, what? Your system has 2 real roots. Correct? When the magnitude of it is less than 1, then you have 2 imaginary roots, or complex roots. Let's write it as complex. And when it is equal to 1, then you have 2 identical real roots, correct? Because both of them will be equal to negative omega n. So, and then you know, when they are identical, when there are 2 real roots, then the Laplace inverse of that portion will be 2 exponentials. When you have 2 identical real roots, it's going to be an exponential plus a t times exponential with negative. And when they are complex, then you have sines and cosines and times an exponential. So we have different answers, and that's what here we are trying to show you, that depending on this damping factor zeta, you will have different responses. So case 1, as I said, it is between 0 to 1. So here we are assuming that it's positive only. And so you have 2 complex roots. If you call these 2 complex roots negative zeta plus minus omega d times I, where zeta is what? Sigma. Sigma is zeta omega n, and then omega d is omega n times the square root 1 minus zeta squared. Okay? So you have these 2 real roots, and you can see them from here too. So this guy, this is called sigma. And then here, if you, instead of zeta squared minus 1, since zeta is less than 1, you write it as 1 minus zeta squared times negative 1. And then square root of negative 1 comes out. It is going to be j. So you can write it as j or I, correct? The complex basis. And then this comes out, right? And then this guy here, omega n square root of what? 1 minus zeta squared, we call it what? Omega d. So in general, you can write it as negative sigma plus minus j times what? Omega d. And that's what I have done here for you. So in this case, as I said, you have complex roots, and the output will be a sinusoidal, which is damped. So it looks like this. Okay? Of course, these are different responses for different zetas, but if you look any of them, that zeta is bigger than 0 and less than 1, these guys here, then the response will be sine or a cosine function where the amplitude of it is shrinking and decaying, okay? So you start from initial condition, and then you start going up. Each one that you go, the amplitude is decaying until what? You finally set up at the value. Now, if it's to a step function, then basically you are settling at 1. Okay, so this value you are settling at here. You're gonna settle at 1, right? So this is y of t versus t. We call this underdamped response here. Zeta is between 0 to 1. Again, the frequency is the same, so this period from here to here is the same as from here to here, and so on. The periods are not changing, but the amplitudes, this one is going to be more than this one, is going to be more than this one, and then this one, and so on and so forth. And you can, if you connect these peak points together, like this one and the bottom ones, you can show that these are the exponential functions, okay? So these are your exponential functions. This is like e to the negative sigma times t, okay? But your general response is like e to the negative sigma times t times sine of omega d times t plus phi. So clearly you have amplitude that is basically shrinking, and the frequency of the oscillation here, omega, this is what? So this is a period, right? One period of oscillation, and you know the relation between period and omega d, right? So omega d is what? 2 pi over 1 period, right? So if you call this t, or this one t, 2 pi over t is what? Omega d. We call it damped frequency of the system. Okay, damped natural frequency or damped frequency. This is different than omega n. Clearly you see omega d and omega n are different, and since this square root is always less than 1, right, because zeta is bigger than 0, so under the square root is less than 1, the square root is less than 1, so you can see that omega d is what, really? It is less than omega n. So if there is damping in the system might still what? Oscillate. But the frequency of the oscillation is less than the case where you do not have damping in the system. So that omega n, that natural frequency, is for where? That is for when you do not have any damping in the system, okay? If you have any damping, any source of friction, anything that wastes energy, you might still be able to have oscillatory response, but the frequency of that is less than the case that you do not have. So if you have a mass spring system, M and K, and if you have a mass spring damper system with the exact same parameters, but you add a damper, like in cars, as I said, a shock absorber. Okay, so in this system, it does oscillate, and the oscillation does not go away. This has sustained oscillation. Okay, so here zeta is 0, and the frequency of the oscillation, which is from here to here, if you call this T1, then omega n is what? 2 pi over T1, the natural frequency of the system. On the other hand, in here, the response of the system, so if you call it X, for example, the natural response of the system is going to be a damped harmonic, right? And then here, the period of oscillation, if you call it like T2, here you have omega d instead of omega n, which is 2 pi over T2, and here zeta is bigger than 0 but less than 1, and omega n is what? Bigger than omega d, okay? So this is the physical meaning of basically damping ratio and everything. And in this system, I can later show you that omega n for the mass spring damper system is the square root of k over m in terms of the parameters, and zeta, if I'm not mistaken, is c over 2 square root k times m. Okay, so I can show you that. So you'll see that in your vibration course if you ever take that course. Anyways, so you clearly see it is a damp oscillation, and now if zeta is 0, which means no damping, then of course you're not going to have any decay in the response, so you will get what? Sustained oscillation, which is this top curve here. You see, it is just 1 minus cosine omega nt. So first of all, the frequency of the oscillations is now not omega n, it is omega d, is omega n, because there is no damping, and then there is no decay, so it keeps oscillating forever. Okay, so hopefully this underdamped case is quite understandable. Now, I told you that there are two other cases, overdamp and critically damped. So overdamp is when zeta is bigger than 0. Then you have two roots with negative real parts, and so your roots are like this: negative zeta omega n plus minus omega n times the square root zeta squared minus 1. The output will be a combination, as you can see, of two what? Exponentials, both with negative. So one of the exponentials is e to the s1t, the other one is e to the s2t, and s1 and s2 are what? These two roots of the denominator, and both of them are negative. I can easily show you both of them are negative. So your response will be like this. There will be no oscillation in it. You start from initial condition and then what? Exponentially converge to the final value of 1. Critically damped is when zeta is 1, so both of the roots are equal to negative omega n. In this case, your response has two parts. One is an exponential, right? E to the negative omega nt, where negative omega n was s1. The other one is going to be another exponential like the first one, but times t. So you have two terms. One is just a pure exponential. The other one is the exponential times a linear term, t. And still, this one will go directly to the output without what? Any oscillation. So, and I can show you, again later, I can show you that actually this guy here converges to the final value faster than overdamp. So if you want the fastest response, which means you reach the final value in the shortest time possible, the best way to do it is using critically damp actually instead of overdamp. This converges way faster than that one. Not way, but quite. And both of them are typically quite getting faster than underdamp, depending on how you tune the system. But the good thing about these two is they do not show oscillation. This one does. Why is it that it's good? Because sometimes you do not need to reach the output value, the input value, the desired value, and then what? Pass it. We call this passing, we call it overshoot. Okay, you should not overshoot. Physically, you do not want to have that, right? Your system has physical limitations that does not allow you, the output, to pass the input, okay? You can just go to 1 or be less than 1. You should never go below 1 because a mechanical or any other limitation does not allow you. So if you physically cannot have oscillations going overshoot, undershoot, overshoot, undershoot until you converge, then you have to tune your system, basically set up the parameters, we'll talk about it later, such that you only have overdamped or critically damped response. This is when you can physically have oscillations. Okay, so I showed you all of that, and now in order to quantify the response of a second order system, we define some performance terminologies. So there are 5 terms we define. We typically use 4 of them, 2 to 5, to basically characterize the behavior of a second order system in response to what? A unit step input. So in general, if this is an underdamped behavior, right? As I said, you start, so here the initial condition is 0. It's not always 0. But you start going, you overshoot, undershoot, and finally converge at, it takes forever, but practically, again, we don't say we need infinite time to converge. As long as you are within a range around the final value, you say, I have gone there, and we call it the settling time. So if we want to characterize the behavior and the performance of the system, there are 5 terms. One is called delay term, which we barely use, but delay time is the time it takes from t of 0 to what? To whenever you reach 50% of the final output, okay? So if you're settling at 1, the time it takes for you to go from whatever initial condition is to what? 0.5, that time is called delay time. We barely use that. Typically we use the rise time, TR. TR is the time it takes to what? To reach to the final value for the first time. So the first time it takes you to reach the final value, we call it what? Rise time. So for an underdamped behavior, we'll see, I'll show you later, there is a formula for that based on zeta and omega n. I can show you how to calculate it. But rise time is only defined for what? For underdamped response, clearly. If you have what? Overdamped or critically damped, how much is your rise time? What's your guess? Because that's the time it takes for the response to get to 1. How much time do you need to exactly reach 1? Yes, you can never reach, right? It takes infinite time, because when t goes to infinity, you settle at 1 exactly. So this is the time that you exactly reach 1. Okay, so before I go any further, I mentioned that for you here. That if the system is overdamped, right? So for rise time, or TR, if the system is what? Overdamped, or critically damped, you will never exactly go to 1. It takes forever. So your rise time is what? Infinite. But if it is critically, if it is underdamped, right, so you have oscillations, then you will reach it, overshoot, and then come back. But the first time that you reach it, we can calculate. How? Well, all I need is, in this response here, that is basically for the underdamped case, I set this whole thing to be equal to what? To 1. Right? If my output, which is this function here, which I mentioned also for you over there, this output, if this output is equal to 1, then I solve for the time. That time will be rise time. Well, the two ones would cancel out. So this term here, this whole exponential, cosine, sine, this whole thing should be 0. And we know an exponential can never be 0 until t is infinite. So the exponential cannot be 0. So the term inside the parentheses should be 0. And here, if you divide both sides by cosine of omega d times tr, here this is going to be 1. That is going to be some number times tangent. And then you solve for tangent of the angle. Okay, and then you take arc tangent to solve for what? For the rise time. And you can show that the rise time is pi minus beta over omega d, where omega d, if you remember, it was what? Based on our definition, omega d was omega n square root 1 minus zeta squared, and beta here is the angle associated with our complex roots. If you remember, in this situation we have two complex roots where their real part is negative sigma, and sigma is this number, and their imaginary parts are what? Omega d. So if I plot those two complex roots in the complex plane, like this is one of them, right? You see, the real part is negative sigma, the imaginary part is omega d. The angle of the vector for that complex number with respect to the negative axis, real axis, that angle is called beta, where tangent of it is simply what? Omega d over sigma, or if you plug in omega d and sigma from here, both of them have an omega n in them, so the omega n's would cancel, so you will get this square root term divided by what? By the zeta term, okay, which is what you can see here, right? So it's pi minus an arctangent divided by omega d, so I write it for you here. It is pi minus beta, and beta is tangent inverse of what? Square root 1 minus zeta squared, the whole thing divided by zeta. And then here is omega n square root of 1 minus zeta squared. Okay, so this is your rise time. As clearly you see, it is a function of both natural frequency and damping ratio. Okay, so when this is specified, it gives you an equation between what? Omega n and zeta if they are unknown. Okay, so the rise time, it is a function of both of these parameters, zeta and omega n. Okay, but again, for overdamp or critically damp, it is practically what? Infinite. So just keep that in mind. Okay, so that is one of the important parameters. Then the other important parameter is peak time. So peak time is the time it takes for the output to reach the first peak of itself. And then the amount of output that exceeds the final value of 1. So how much would you exceed or overshoot the final value, the difference between max and 1? This difference is called what? Maximum overshoot. Okay, which you typically write it in percentages. So let's say if it's 0.2, so you went 0.2 above 1 unit. So how much did you overshoot? 20%, right? 0.2 divided by 1. Or if you go up by 0.5, so your final value is what? 1.5. How much did you exceed 1? 0.5. 0.5 divided by 1 is what? 50%. So typically they say this MP in percentages, okay? So 60% means what? Means your maximum value is 1.6, okay? So maximum overshoot and what? Overshoot time, right? Or sorry, peak time, TP. How do I calculate those? Again, that's not hard. What's specific about the peak point? Well, at peak point you have a max. And you know from your calc courses, at max, the value of the derivative is 0. So if you take a derivative from your function and set it equal to 0 and solve, you can find out that Tp is simply pi over what? Omega d. So it is very similar to the rise time. Okay, it is very similar to the rise time, except you don't have this arctangent part. It's simply what? Pi over omega d. So it is very similar. Again, you don't have this arctangent part. It's very similar to that. Okay, and then maximum overshoot is you have to plug in this Tp, right? You have to plug this Tp back into your y, find how much y is, subtract it from 1 to get MP. And that's what here is done. So we calculated the output as the peak point minus 1, and if you simplify, it is going to be e to the negative zeta pi over the square root, okay? So MP is an exponential of negative pi zeta divided by what? 1 minus zeta squared under square root. So as you can see, rise time and peak time, they are a function of both zeta and omega n, but MP is only a function of what? Zeta. There is no omega n in it. It's just a function of zeta. In other words, if I give you an MP from here, you can directly solve for what? Zeta. How much is zeta in terms of omega p, the inverse function basically, which is what I have for you over here. It's the square root of natural log of MP, correct? So it is natural log of MP, the whole thing squared, divided by the same thing, plus what? Pi squared, okay? Okay, again, my pen is not writing. Let's see. All right, and clearly you might say, okay, what about the cases of overdamped or critically damped? Well, if you look, would you ever reach a peak? No. How much is your final peak? Nothing. You will never ever get that, okay? So if even you do, your max is gonna be 1, okay? It takes forever to reach your peak, which is 1, and at there your function is 1, so the difference is 0. So for those cases, if I want to mention them, again, T of P is also at infinity, and MP is literally what? 0. Okay, so those cases of overdamped and critically damped, we really never specify these parameters. As I said, these important parameters, T rise, T peak, MP, and later the settling time that we talk about in a second, these are all defined for underdamped response. Okay. So the last parameter that we define for performance of response to a step input of second order systems is settling time. As I said, really it takes forever for any of these responses, over, under, or critically damped, to get to 1 and exactly stay at 1. Okay, so the other two it will take them forever to just reach 1. This one will reach 1, but it does so much of overshoot and undershoot that it takes it forever to settle at 1 and not overshoot or undershoot anymore. And we practically, in any application, we cannot wait forever. So what we define is a settling time. And settling time is basically the time it takes to reach in a neighborhood of the final value, very close to it, and never leaving that zone or neighborhood around it. So let's say if I'm 2% error around 1, so I'm anywhere between 0.98 to 1.02, then I call it a settling time of 2%. Or if I'm 5% around it, so between 0.95 and 1.05, then I call it a 5% settling time. And then I can show you, again, mathematically, it's easily doable to show that if you want to reach to 2% around the final value, then 4 times time constant of the system. In this physical system, in a second order system, the time constant, if you define a time constant for this system, it is 1 over sigma. Okay, 4 times time constant, you will reach to 98%. So we are making the second order system similar to a first order system. If you remember, first order system, it took it 4 time constant to reach within what? Less than 2% error of the final value. So if you make a second order system be similar to the first order, basically, if you say these are similar, you can define a time constant of 1 over sigma for this system, because that's those two exponentials that I said they are the envelopes of the decaying sinusoidal. So for those, you can define a time constant, right? How can I do that? Just so you might be curious. So if you look at the response here, this is the harmonic part that is oscillating. The exponential part that is decaying and makes the amplitude decay is e to the negative zeta omega n t in general, right? It is e to the negative zeta omega n t, correct? So those two exponentials, we call them envelopes of the underdamped response. The power of the exponential is negative zeta omega n. And what is zeta omega n? Based on what we define, zeta omega n is called what? Sigma. So those exponentials are like what? E to the negative sigma times t, correct? Now, in a first order system, how was the response? In a first order systems, your response was e to the negative t over t. So you want to say this is equivalent to what? E to the negative t over t. So now if you compare t and sigma, you see that t for the second order system is what? 1 over sigma. And so 4 time constant, it took it to reach to more than 98% or within 2% of the final value. So here, basically, if I want to reach to within 2% of the final value, I need 4 times constant, which is 4 over sigma or 4 over zeta omega n. If I want to be within 5%, again, I go back and look at that graph. So 5% is what? 3t. And if I want to be reaching within 1%, then I need 5t, okay? So when they specify settling time, they always tell you what criterion. Is it a 2% criterion, 5%, 1%, or so on? The typical one that is used most of the time is 2%. So if you want to reach within 2% of the final value and never leaving that zone or that area, it takes you 4 over zeta omega n to make it happen. So my last parameter here, as I said, it is called settling time. With a 2% criterion, it is 4 over zeta omega n. Again, as you can see, settling time is also a function of both parameters, zeta and omega n. So all of the times, t rise, t peak, and settling, they are all functions of zeta and omega n. The only one that is pure zeta is what? Maximum overshoot, which again, we typically, don't forget that, we define this guy in percentages. Here, this formula is not going to give you in percentages. This is just going to give you a number which is less than 1, typically. Okay, so this is going to give you like 0.5, 0.6. So if you want it in percentage, what should you do? You have to multiply this number by what? By 100%. So if it's 0.5, it means 50% overshoot, correct? So just keep that in mind. So that is the settling time. Now you might wonder, what about these two cases? What's the settling time here? Well, that's the same thing. Basically, they act very similar to a first order system. So for these guys also, it is going to be what? 4 over t. The only thing is, what is t for this case? Okay, what is t for this case? And so if you look, you have two exponentials here, not one. One of them is s1t, one of them is s2t, and s1 and s2 are these guys. And one of these guys is bigger, one of them is slower. Both of them are negative, right? But like one of them is -5, the other one is like -8 or something, -6. So which one is the determining factor? The one that is smaller. Why? Because if you plot exponential -40 and exponential -80, which one will converge to 0 the slowest? Of course, the one with the smaller exponent, right? If you have a big exponent like -20t, -30t, it just needs a little bit time for it to very fast converge to the final value. So the smaller one, and by smaller I mean the absolute value of it, that's the dominant one, that's the one that determines. So one of these two is the smaller. Which one? Clearly, this negative zeta omega n is a negative number, and this guy here, the second term also, now this one is a positive number because zeta is bigger than 1. So the first term is negative, the second term is positive. So which one is a bigger absolute value one? Of course, the one that is negative, right? So because it's like -4 minus 2 and then -4 plus 2. Which one? Yeah, one of them is -2, the other one is -6. So the smaller one, which has this plus sign, that is the determining factor. That is going to be the exponent, okay? So if I want to define something for these systems as a settling time, the settling time is 4 over sigma, or 4 over the exponent, basically, 4 over the exponent, and exponent is here what? Basically, we want just the absolute value of it, which is zeta omega n plus omega n times 1 minus zeta squared, the absolute value of this guy. Okay, the absolute value of this is going to be your exponent, and the inverse of that is going to be the time constant, and 4 times constant is your settling time. So if you want an actual settling time for overdamp or critically damped, that's what you should use. Okay, that's the only thing that is not 0, not infinity for a critically or overdamped system. You can actually define a settling time, which I mentioned here for you. Okay, so we went over lots of things. Now, in many examples that you solve in this chapter, they give you some of these performances, like they give you a settling time and the maximum overshoot or something, and then they ask you what is the transfer function, right? Well, if you want to find the transfer function, the only 2 parameters unknown in it are what? Zeta and omega n. So if you know zeta and omega n, you know the transfer function. How do you determine zeta and omega n? Well, zeta is easy. If they give you maximum overshoot, then you can directly calculate what? Zeta from the percent overshoot, right? You directly come and use this formula, and it gives you zeta. Then let's say they give you a settling time, right? So once you know settling time and zeta, from there you can solve for what? Omega n. Or they give you like a rise time and maximum overshoot. Again, once you know zeta, the only unknown here will be whether they give you rise time, peak time, or settling time. The other unknown is omega n, so you can determine omega n. Now, sometimes they might not give you maximum overshoot. They might give you a rise time and a settling time. Then you will have 2 equations. One here between zeta and omega n, and maybe one here between zeta and omega n, okay? So it depends on what they give you, but they typically give you 2 parameters, and you have 2 unknowns, zeta and omega n, that you need to solve, and then you determine your transfer function. Let's look at an example together. So here, this is problem A54 of your textbook. It says determine the values of cap k and small k such that the closed loop response of the system below shows a maximum overshoot of 25% and a peak time of 2 seconds. Assume that this inertia, moment of inertia J is 1 kilogram meter squared. Okay, so J is simply 1. So in this case, 2 seconds peak time, 25% overshoot. So let's look at this guy together. So we write it. We want a maximum overshoot of 25%. We want a peak time of 2 seconds. This J here is 1 kilogram meter squared. Let me write it down here actually. And you need to find cap K and small k in this system. So you have two parameters that you can tune, you can change. You want to change them such that the second order system, in response to a unit step input, shows such behavior in the output. Yes? By the way, I added those performance basically metrics for the overdamped and critically damped systems as a slide to your lecture. Okay, so just wanted to have complete notes. So going back to this problem, first thing is we need to find the closed loop transfer function, right? So clearly know that these two are a loop already. So the equivalent to these will be G, which is in this case K over JS, and J is 1, so we're just going to write it as K over S. Divided by 1 plus small k times K over S, which if you simplify it is going to be cap K divided by S plus small k times cap K. Then that thing will be multiplied by 1 over S because now it is in series with 1 over S. So now you will get this one. And then that transfer function with a feedback of 1 again will be in a loop. So it is going to be now the new G function, K over S squared plus K cap KS, this is your G, over 1 plus the same thing times 1, which is now the new feedback function. Which again, if you simplify it, is going to be cap K over S squared plus K KS plus cap K. Okay, so this is your transfer function G of S, or you can say this is, in this case, C of S over R of S, right? This is your final closed loop transfer function. And if you compare this against the standard form, omega n squared divided by S squared plus 2 zeta omega n S plus omega n squared, you clearly can see that your cap K is omega n squared, and then 2 zeta omega n is a small k times cap K. Okay, so if I can find my zeta and omega n from the performance metrics, I plug them back here, I can find small k and cap K. Now, how do I find them? I find them from MP and TP. So MP is 25%. So MP is 25%, which means in decimals it is 0.25. This is equal to e to the negative pi zeta divided by square root of 1 minus zeta squared, right? As we learned here. And so then we can plug it back into the zeta formula and say that's the square root of natural log of MP squared divided by that. So let's first get zeta. So from here, zeta is going to be square root of natural log of 0.25, the whole thing squared, divided by pi squared, plus, again, the same thing, natural log of 0.25, the whole thing squared. So if I calculate that, right, in MATLAB, you know, when you say log, log is natural logarithm. If you say log 10, then that's log 10, but log itself is natural log. So that's this number, and then if you square it, that's this number, okay? So now you say square root of this number divided by the same number plus pi squared. So 0.4037. Now in this course, 2 decimals is enough, so we just go with 0.4. So your zeta is 0.4, and clearly you see this is less than 1. Otherwise, you cannot have a peak time, right? Because if it's not underdamped, there is no peak time, it's infinite. So make sure whatever zeta that you get out of this formula is necessarily less than 1. So that's your zeta. Now T peak, if you remember, T peak was what? Pi over omega d, correct? So we can go back and find it. It was pi over omega d, or pi over omega n times square root 1 minus zeta squared. This is 2 seconds, and zeta is 0.4. From here, you can find what? Your omega n, which is going to be pi over 2 divided by that square root, correct? So pi over 2 divided by square root of 1 minus zeta squared. I guess I got one extra. 1.71 again, if we round it to 2 decimals, 1.71 radians per second. So now that I got 1.71 and 0.4, I come back here. So this is going to be 1.7, how much? 71. So 1.71 squared, right? So I can get my cap K. .92. And then from here, small k, it is going to be 2 zeta omega n divided by cap k, right? So 2 zeta omega n, 2 times 0.4 times 1.71 divided by 2.92, 0.6. So if you round it, you have to get 0.47. So these two are the solutions. Okay, so that is how you tune these parameters to get those performance characteristics for this physical system.